In this video, I'm going to talk about vector decomposition. Let me share this screen. No, let's go this one first. So vector decomposition. Vectors, which contains the quantity of magnitude and a direction. So we know that any arbitrary vectors, you have you just draw any random vector arrow, right? Random one. So let's say this is F, vector F. Vectors can be decomposed into perpendicular components. So instead of seeing this just one vector F, you can see that this F vector is made of this vector, let's see. Fx and made of Fy. So we can say that F is exact the same thing as Fx plus Fy. So Fx plus Fy is the exact same thing as looking at one vector F. It's useful to decompose the vector into two perpendicular components to talk about physics. So let's see. Let's do the case like this. Here is dog on a sled. Here's a dog on a sled. And Nellie Nelson is pulling this sled. She's pulling this sled with some angle in this direction. So then what would be better for her to pull this sled? Horizontally or more vertically? We can decompose this F force, the force F that's being pulled, into one that horizontal component. Fx and then Fy, right? And so this sled has the pull force from Nellie with F force that's been pulled. And then what else are the other forces? What are the other forces exerted on other forces exerted on a sled and a dog? Right, we do have gravitational force, right? We have a gravitational force, vertically downward, Fg, and normal force. So that would be Fg and the normal force. But are they equal to each other? Are these equal in magnitude? No, right? Because the normal force now is going to be a little bit less. The net force on the y direction. So one good thing about decomposing a vector into two perpendicular components is that you say if the total net force is 0, that means Fx is 0 and Fy equals 0. So you can see the motion into the horizontal component and the vertical component independently. They don't depend on each other when they're perpendicular. So any motion that's only in a vertical component, you can just look at it only in this direction. In this case, we don't think that sled is going to go up and down. It's just going to go maybe only in a horizontal direction. So Fx is not 0. In this case, it's Fx is not 0. In this case, this example, net force on the y direction is 0 because the sled doesn't go moving up and down. That means that, what is it? Normal force plus, this is confusing. The force Fy, which is this force. Sorry, it's confusing. Fy, this force, minus Fg is equals to 0. So now the normal force will be less than Fg because you have a help from the force that's pulling by Nelly. This is the force from Nelly. She's holding a tie. Right? So normal force is less than her. So in this case, normal force is less than Fg and is not equals to the gravitational force. Sounds good? Okay. How about, so we've been doing this thing, it should be really easy. Let's think about a case that how the normal force changes on let's say block of ice on the horizontal surface. Then what are the forces exerted? Gravitational force, vertically downward, next door neighbor. And then have a normal force, vertically up. And this is equal and opposite to each other. But what happens when you tilt the plane, right? When you tilt the plane, the gravitational force does not change, always vertically downward, right? And then you decompose the gravitational force into the vertical, perpendicular to the surface, parallel to the surface. Fg perpendicular, Fg parallel. Therefore, normal force which is going to be the response force onto the perpendicular component, this one, is going to be equal. So normal force decreases right? And what is it? When it completely become vertical, gravitational force doesn't change, still mg, vertically downward, right? But all the components is Fg parallel. Fg perpendicular is 0, therefore normal force is 0. So when there's no normal force though, when there's no normal force, this is what is the net force? There's no normal force. Net force on this is gravitational force only. If it's only gravitational force applied on an object, what is this called? It's called free fall. So it's in free fall. Acceleration equals to g. And you can see that, right? Let's look at an acceleration here in the inclined plane. Acceleration is equals to net force. But in this case, the motion is in this direction. This is the motion, parallel component to the surface. So there is acceleration on the perpendicular component is obviously 0. But there is acceleration on parallel component that's equals to the net force on the parallel component divided by its mass. And in this case, parallel component that's equals to Fg parallel divided by mass. Right? And you see that sorry. Yeah. And you see that that's that. So that's why here, right, A parallel is equals to Fg parallel divided by M, and that's equals to Fg. So that's G. So we've been doing this over and over, and for this video, we applied everything. Newton's second law of motion, we applied vector decomposition clearly. Also the Newton's third law of motion that says the normal force is the response force from the Fg perpendicular, because normal force is a perpendicular component. Okay, dokie. So yeah, let me see. Hope you can answer this question. Slideshow. Here. Two forces act on a block of ice. As the ramp is raised, which force remains constant? Okay. As the ramp is raised, how does the magnitude of N change? Okay. When the ramp is raised 90 degrees, completely vertical, what is the net force on the block? The motion is called. All right. Therefore, the acceleration of such an object is. All right. So that's it for this video. And I'll see you in a class.